Yes, Professor.
Yes, Professor.
You do, right? Okay, Gautam, you can start recording now, or if it's already started, that's fine.
Yeah, I just started.
Okay, so we are going to start on what is called the wheat trading model. And the reason for wheat trading model is not so much is to trade in wheat because it's a deterministic model. There is no randomness here, and you know the commodity markets are not exactly deterministic. However, this problem was first proposed by two professors at Carnegie Mellon named Ijiri and Thompson. Yuji Ijiri was a Japanese professor in accounting, quite well-known guy, and Thompson was my advisor. And they published a paper in Accounting Review, which was the top journal in accounting review. And they they published this model used to demonstrate the use of control theory in accounting. And the Accounting Review was happy to publish that paper. When I came upon the scene, I realized that the wheat trading model was, while it was very simple, it allows us to demonstrate in a very nice way the idea of what we call decision and forecast horizons. And we'll talk about that later. So let's begin with the wheat trading model. We have a finite time, and we are going to trade in wheat. So we have a price forecast PT. Again, it's a deterministic forecast, so I just warn you, this is not a real life problem where you would have to have a price stochastic. By the way, this is very similar to the cash balance problem that we did in chapter 5. And we have generalized the cash balance problem to stochastic demand in a paper that I wrote with Ben Susan and Sandun Pereira, who was a student here a couple of years ago. He's just received his tenure at University of Utah in Lake Tahoe. If you ever want to visit Lake Tahoe, do contact Sandun. He's your school brother. Okay, so the price of wheat is known to us, the forecast, and basically what this paper demonstrates, or this model demonstrates, that you sell high and buy low. There's a stock market's dictum saying buy low, sell high. But of course, buy low, sell high is very interesting and easy to manipulate if you have a deterministic forecast, so you know when the price will be high and when price will be low. But if it's stochastic, buy low and sell high is not exactly the way you can just implement. You require some more sophistication to implement that. So the idea is to buy wheat when the price is low, sell wheat when the price is high in order to maximize your profit. R is the constant positive interest rate earned on the cash balance. XT is the cash balance in dollars at time t. YT is the wheat balance in bushels at time t. VT is the rate of purchase of wheat in bushels per unit time. A negative purchase means a sale. And HY is the cost of holding Y bushels of wheat per unit time. So there is a storage cost, which happens in all kind of inventory model. So this is kind of a mix of inventory model and a cash balance problem. X dot, which is the balance of cash, is going to have this kind of a state equation because we are earning interest rate R on cash, so that Rx is incoming interest. We must pay the storage cost on Y bushel of wheat that we have right now. So that's the cost we have to subtract. And then if V is, now remember now, V is the rate of purchase, minus V means sale. So if we purchase the wheat, we are going to use the cash to purchase the wheat, so that's going to reduce our X dot. On the other hand, if if we sell the wheat, the V will be minus, so we are going to get positive cash flow, and that means the X dot will increase. And we have initial cash balance of X0. Y dot is V, which is the rate at which we purchase the wheat. So it goes up when we purchase, and it goes down when we sell. And we have initial balance of wheat in our warehouse, which is Y0. In order to avoid impulse controls, which means buy infinite rate, which basically means buy a finite amount of wheat instantaneously. And that gives rise to the impulse control, and we are not going to do that. So we're going to bound the control constraint, which means we're going to bound the rate at which purchase. We cannot purchase faster than V1, and we cannot sell faster than V2. Just as in cash balance problem, we can either compute profit at each point in time and integrate it, or we can just say maximize my final wealth, which is the amount of cash plus the valuation of the wheat at final time P of T. Okay, so those are equivalent. But this is a Meyer form. It's a linear Meyer form. But we also know that Bolzan form is equivalent to Meyer form mathematically. But we also now know that if you maximize the profit, it gives you, and you integrate the profit at each point in time, then you get the Bolzan form. And if you maximize the terminal wealth, you get the Meyer form. But you know that they will be equivalent intuitively. But we also had shown in chapter 2 that mathematically they're also equivalent. So I'm going to take the Meyer form. Hamiltonian function h equals to lambda 1 rx minus y minus pv plus lambda 2 times v. It's standard. Notice at this point, I have no constraint on x and y. There are no state constraints at this point. When we have no constraint on y, it means we can short sell wheat, which means that we can sell the wheat we don't have and then buy it later to cover the position. Lambda 1 dot and lambda 2 dot are standard. They're just the derivative of the Hamiltonian with respect to x and y, minus of those. And we can easily solve them. And since we don't have the form of hy, and as well as prime y, we can only show that's an integral. But if I give you hy, we can maybe be able to integrate that and present you a better form. So now the solution is bang bang. Depends on the coefficient of the control v in the Hamiltonian, which is given by this. And so we have a bang bang control. So what I will do now, the problem is solved. This is the model of Ejiri and Thompson, and this was presented in accounting review. And now what I do now is beyond that. But to do beyond that, I want to simplify something. You could not simplify it and just make a more difficult exposition. But for my purpose at hand, I will simplify it. Now remember, while I'm giving decision and forecast horizon, by using this, I'm also teaching you for the first time state constraints. We did the state constraints in chapter 4. We did some examples and problems and homework. But now we are actually utilizing the theory of chapter 4 in an actual model in finance or production or inventory. So let us go through a simplified version of this example. We will assume that the storage cost is half of absolute value y. Half is just there so that when we I don't know whether there's an integral somewhere and then a half gets canceled, but it doesn't really matter. We just I think it's possible that when you do y square, then you need this half. So there may be somewhere a comparison of this model with y square. But in any case, we do what we want. And absolute value of y means that the cost of storage is symmetric to the cost of backlog. That means when y is negative, we also pay because we have a backlog, and there's a backlog penalty. We cover the model, we cover the short sale, but there's a cost of carrying a backlog, which is symmetric, which is very, very common in inventory literature, although sometimes it's not symmetric, but that's okay, we can handle that. Right now, we are not going to do that. And we begin with the 10 unit of cash, $10. We begin with no wheat. We set our upper bound and lower bound by 1. We set our T equal to 6. And we have a price forecast. The price forecast is just simply this. Its price is 3. And at some point, which is time 3, it goes to 4. So it's a good idea to buy the wheat now and then sell the wheat here. That is very simple here. But now we have to find out, given all the problems that we have to find the solution of this problem. And so we're going to do that. We're going to assume r equal to 0. Again, to simplify, it's a 6-period problem. So interest and cash, it's not going to, mathematically, it's not going to change anything. And it'll simplify our expressions. When r equal to 0, this becomes 1. So lambda 1t is identically equal to 1 for all t. So we already have lambda 1t equal to 1. And then these equations that we have simplified, these are our state equation. Notice that we had assumed our functions to be continuously differentiable. This is not the case here. Y absolute value is not continuously differentiable at 0. But there is a way around it. One way, there are two ways around it. One way around it is to develop another maximum principle for functions that are not continuously differentiable. And there is a theory of non-differentiable functions, and there's a maximum principle for it. It's a little bit more mathematically challenging. And one reference for that, which is convenient, is a paper by me and my former postdoc, Richard Hartle. So there's a paper by Hartle and Sethi somewhere, cited, I think, in the book, which gives you a non-differential maximum principle and an application of that in inventory context. The theory has been developed by somebody like Clark, and there are others. And those are published in math journals. And again, they are cited in this book. The second way around is a cheap way of doing that, which cannot always be done, but in our case, it can be done. And that is that we will use this because it really happens only at one point. And when we take the derivative of this, we call this function a Signum function, which is the sine of y, which means when the derivative, so that function looks like this, okay? It's like slope of 1 this way and slope of 1 on the negative side. So its derivative is 1 on this side and minus 1 on this side. So at 0, when y is 0, that function is kind of not defined. But since we're going to integrate, 1 point won't make any difference, at least in this setting. And so this means that when y is positive, this sine y means 1, because it's derivative of the positive y, which is 1. And when it's on the other side, y is negative, then the cost is half of y, half of minus y, because y is negative. And so its derivative is minus 1. So signum y means +1 when y is positive, -1 when y is negative. So this will be plus half and minus half, depending on the y being positive or negative. So this all proper. And the value control is basically -1 + 1, and this is the coefficient of the v in Hamiltonian. And so this is something that you know by now by heart. It's a bank control. So now comes the intuition and insight. In order to solve this problem, notice that state constraint problems are notoriously difficult. Right now, we don't have a state constraint, so we're starting out without a state constraint, but we will eventually quickly go to state constraints in the next section. And we will see that we are going to be able to solve this problem completely, explicitly, but it is because we are going to use a lot of intuition, a lot of guesswork, and then use the maximum principle to verify that our guesswork is optimal. Notice, if PT is increasing, you would never short sell. So in our model, short selling is not allowed. Not allowed is not going to be optimal because the price is low now. So if you sell now, then you're going to sell at price 3. So you don't have any wheat at time 0. So if you sell 1 unit of wheat at time 0, you're gonna only get $3, but you must cover your position before capital T. And if you cover the position at capital T, you have to pay $4 to get the same amount of wheat. So you lose $1 in short selling, and then you also lose a backlog cost of half per unit time. And so you can see the short selling is never optimal. Since the storage cost is half per unit of time, and the wheat price only jumps by 1 at t equal to 3, clearly it never pays to store wheat more than 2 units of time, because we will only gain $1 by buy low, sell high dictum, but we will pay storage. And if I buy something now and sell it 2 periods later, then I have eaten up my gain simply by paying the storage fee. So it never pays to store wheat more than 2 units of time. And since wheat price changes at exactly 3, at time 3, you will never want to buy the wheat at time 0. Because if you buy 0 wheat at price $3, then you will sell it after time 3. You will have spent $1.50 in storing that wheat, and you will only gain $1 by selling that wheat. So we will never buy the wheat at time 0, but we will never buy the wheat even before before what I mean by is that we don't want to buy any amount of wheat and sell it more than 2 units time later. So suppose we start buying wheat at some time bigger than 1. Okay. Then the rate of buying is 1. And clearly the buying will continue at this rate until t equal to 3 and no longer. And in order to not lose money on the storage of wheat, it must be sold within 2 times unit of its purchase. So it's not going to happen at 1. I'm saying t star bigger than 1. So it's going to happen at some point in time. We're going to find that out like this. Clearly, we should start selling wheat at t equal to 3 plus. Now, notice we cannot impulse sell. So we can only sell at a rate. So we should start selling at T just after 3. And we're going to, by Big Bang principle, we're going to sell at the maximum rate of 1. And we continue selling until the last sale time T double star. And in order to sell exactly all of the wheat purchase, because there's no reason to keep, so you see, if I don't want to keep the wheat, I want to sell all, whatever I want to buy here, I want to sell here. Because if I don't sell some, I will have to carry it all the way up to here. I will incur the cost of that backlog, not backlog, but if I carry some, I will incur the cost of storing. And when I incur the cost of storing, what is going to happen to our terminal balance? Our terminal balance will have the same amount of wheat, and it will be evaluated 5.4. But some of those wheat, some of the backlog costs will be paid, and our XT will become lower than if I did not have any wheat to carry all the way to capital T. So this will, some of the storage costs will be eaten up, and our cash balance will go down. So we will not be able to maximize our terminal wealth. So given that, it is clear that amount of wheat that we would buy from 3 minus T star should be sold from T double star to 3. I mean 3 to T double star. And so we can say that V star T to 0 after T. So from T double star to 6, V star is going to be 0, which will be a singular control. Okay. And if I do this policy, then the amount of wheat will be bigger than 0 between T star and double T star. And the lambda 2 dot is half in the interval. So I can actually, so this is kind of intuition, and then we're trying to do the math. So in order to have a singular control in time T star 6, I must have lambda T 2 T exactly equal to 4. Remember, singular control requires that this is 0. So the lambda 2 T will have to be equal to PT at some point in time. And if I want to have the singular control begin at T double star, then lambda at T double star would have to be 4. But remember, there'll be a singular control before T star as well, because I'm not buying anything for a while until T star, and I'm going to sell all the things by double T star here, T double star here. So all the action will happen from here to here. I'm trying to find out what that point is and what that point is, but here will be singular, here will be singular. So here the lambda 2 where it will be singular will be 4, lambda 2 here singular will be 3. So we know that the difference between these two guys is going to be exactly equal to 1. Right? But the lambda 2 dot is half. And so we know it's going to increase, but the increase can only be equal to 1 in that amount of time. So the amount of time in which that increase will happen at this rate half cannot be, it has to be exactly equal to 2. Because in 2 unit of time, if you go by the rate half, then you will increase the whatever the variable would be by 1. So we have another equation which is 2, and we have another equation which is already equation which is this, and we have 2 equations in T star and T double star, and they are easy to solve. You know that there are 2 equations, 2 variables, linear equations. So we get T star equal to 2 and T double star equal to 4. Of course, if I did all of that in a picture, it'll be a little bit easier to explain, but I thought that I want to do it this way right now, and then I will look at the picture. So if I did that, all of that, then we know that lambda T will be 3, lambda 2 will be 3 up to 2, because remember this is 2, T star is 2. So it'll be 3 up to 2. At 2 will be exactly 3. Then it's increased by half at the rate of half, so it will be this formula up to 4. And after 4, it will be exactly equal to 4, because at 4, it will become 4, and then we'll stay at 4 because the singular control up to 6. So you see, we got everything here. And now we can see this in a picture. So what was our intuition? Our intuition was that we should buy the wheat at some point in time before 3 and sell all of wheat after 3 at some point in time, by some point in time. We don't want to carry anything to incur the holding cost. And we don't want to do anything here because whatever I buy here will be sold here, which will be more than 2 time units later. So all of that is very clear. Once that is very clear, we need to find that time T star and that time T double star. For that, I use 2 things. First, I use the fact that these guys are singular. Lambda 2 is singular here and there, so I know its value. And it's increasing the rate half. And so its increase has to be exactly equal to 1 from here to here. So it has to go from 3 to 4. So if you go from 3 to 4, it goes like this. So we know what that means. This has to be 2 time units. And it has to be symmetric because we are selling at the rate 1 and buying at the rate 1. So if it's 2, if the entire time is 2, then lambda 2, that interval of 2 has to be split by this time 3 equally. So that portion has to be equal, which means this portion has to be 1 and this portion has to be 1. So that's how we got all of that. And then when we got all of that, we know that when we buy the wheat at rate 1, I had a 0. When we buy the wheat at rate 1, I will just keep buying until I get here. By that time, my unit of wheat will be 1 bushel. And then I will sell 1 bushel at the rate half all the way, and I will have no wheat left at this time 4. And then I have nothing to do nothing. And so this is our solution, explicit solution, which is really easy to see that this is an optimal solution. It's maximized, satisfies all the conditions that we want. Now comes the part that I am working on here. So I'm now saying I don't want any short selling. Remember, short selling would be possible if I reverse the price. If I put 4 here and 3 there, then I would short sell here and recover the position buy here. I mean, this will be flipped. So I'll be buy on this side and sell. So it will be exactly symmetric. But I will have to allow Y to be negative when I short sell. And for that to allow negative, I have to have this function to be this function to be this function, because Y is negative, but I'm still paying positive amount of money, so I need the absolute value, or I need quadratic function if you want, depending on how the cost is incurred. But now I disallow short selling. So in this model, the short selling did not happen simply because of the price trajectory. It was allowed, but it didn't happen. Now I'm disallowing it. When I disallow it, then I can write hy equal to y divided by 2. I don't need absolute value anymore because y is not going to be negative. And if y is not going to be negative, the absolute value is exactly equal to y. It's linear. But now I give you a different price forecast. I make it more interesting. So t equal to 3, price forecast is like this. It's decreasing, then it's increasing. And so my problem can be written as this way. My terminal wealth is x3, p3, y3, which is 4 times y3, because if you look at the price exactly, price at capital 3 is 3 plus 1, which is 4. So this is 4. This is half y, now no absolute value. And this is y dot v, y is equal to 1. Now I start with 1 unit of wheat instead of 0 unit of wheat. And this is the condition because I am not, this is the condition on control, but now is a state constraint. Y has to be bigger than equal to 0 because no short selling is allowed. This kind of model is easy, but to present that in a class, it becomes easier when you have already read it before. If you don't read this before, the presentation for me becomes more difficult because I have to go back and forth from all these equations that are going to be used one after the other. And it is not easy to flip slides. I mean, you can, but it is just takes too much effort, and it's also not very convenient. And so you will see what happens if you read the chapter before. That's a lot easier. If not, then you learn less. The Hamiltonian is given by this. The optimal control now has two forms, two formulas. One is when y bigger than 0, it's the same as before. But remember, when y equal to 0, I cannot do -1, so I can only do 0. So there are two bang bang here, because whenever y equal to 0, we must impose y dot equal to v, which is bigger than equal to 0. And so we cannot use -1, we have a 0. And then because we have a y bigger than 0, we are doing indirect maximum principle in the rest of the book, although in chapter 4 I did both because many papers do this or that. But I have done in my book an indirect maximum principle, partly because mathematically it is easier. So I have eta v. And because I'm doing Lagrange principle, I also need mu1, mu2 for these constraints on v, which are -1, v less than +1. So we need those two constraints. So we have a Lagrangian. And in problems like this, you see Lagrangian means many variables and many equations, and all of them have to be, used in one way or another to find everything. In mathematics, it turns out that you sort of have to be in a Goldilocks region, in the sense that every equation that you have, somehow or the other will be used. It is not. It's just one of those things. There's nothing there that's just sitting there for doing nothing. So there are a lot of equations, and each one of them has some role in. So like all of these inequality equations. So you see, already we have 6 of them, and every one of them has some role. And so when we find all these variables, we need almost everything one by one in some way, and how you use them is part of research. Delta L delta V equal to 0, so we have another equation. Then because R equal to 0, lambda 1 is before lambda 2 dot is this. We know this equation. And then we have lambda 2 3 is 4 plus gamma, because we are using we are using what is the maximum principle in 4.29, where we do indirect maximum principle, which 4.29 in chapter 4. Now you can see, if you were reading at home, you would go back to chapter 4. If I'm doing it here, I have to go to the book because I don't have the chapter 4 slide in front of me, but I can easily go to the book. But then I have to also give you stop screen sharing and do a new screen sharing and all that stuff. Okay, so, and then there's a complementary slackness condition on gamma. So you see all of these equations, there are quite a few All of them is going to be used in getting the solution. So this is reminiscent of another problem we did before. So let's continue. We're going to make two guesses of gamma. And one is gamma equal to 0, one is gamma bigger than 0, and you know my style. I'm going to use the guess that's going to work, and gamma bigger than 0 is not going to work. But if you were to begin with gamma bigger than 0, you will see that all of these equations will not be satisfied. Somewhere you will have a contradiction, and that contradiction says, okay, that guess is no good. Then you have to go back to gamma equal to 0. It might be a good idea for you to do that at home, but usually you don't do this in textbooks. Okay. If gamma equal to 0, then lambda 2, 3 minus equal to 4. And so now we want to know where there would be a jump. Because remember, in chapter 4, there may be jumps. And if there are jumps, the 2-point boundary value problem cannot be solved unless we know jump in between, because otherwise it doesn't work. So let me now tell you what I'm after by going to a figure. And of course, when you don't have a figure, you have to go like this. But at some point or another, you should start drawing the figure and put whatever you have into the figure as you go along, so that your ideas are becoming a little bit more easy to implement. So let me go to the figure and show what we can do so far. See, again, quite a bit. So here's the figure. So this is the figure. And I'm going to plot price forecast, which is this line. It goes from 7 all the way to this point, and the price increases all the way up to this point. This is our price forecast. And we started lambda 2. This is the lambda, that the bold face is lambda 2. We're not there yet. We are only here. We are at lambda 2, 3 minus. This is 3 minus. This is a plus, but 3 minus is also 4. And 3 plus, the gamma is 0, so 3 plus is also 4. But otherwise, we just begin with 3 minus, okay? So and we know the slope of lambda is like this. So if there were no jumps, that lambda 2 will go like this all the way up to here. And we are done. And once we know this, we know that when lambda is above the price, we do one thing according to bang bang. If it's below the price, we do the other thing according to bang bang. So our V star will be done. So if it's above the price, we buy. If it's below the price, we sell. And if y equal to 0, if you don't have a wheat, we do nothing, because that's another bang bang. So all of that, once we do lambda 2, so suppose there was no jump, lambda 2 can be done like this all the way up to here. Once we know lambda 2, we will know V star. Once we know V star, we know y. And once we know y, we will know where we do nothing. Okay, so problem becomes easy. But now there's a jump. If there's a jump, we cannot just go like this. We need to know where the jump is. And that is the $64 question. And that's what makes chapter 4 difficult. That's what makes the control theory of state constraints difficult. So we have to do a lot of work to figure out how to manage this idea. How to find this point 1 where the jump is taking place. Okay, we already know this point, because if there's no jump, we know that there's not going to be jump. Okay, we know that this is the time at which lambda 2 is exactly equal to p. So this is the time where you can have a singular control. So this is the time where the singular control may end. And if it may end, then somewhere along the line, y was 0, and we entered the constraint y equal to 0 somewhere here, and we want to find out that somewhere here. So we start here, then we go here, then we go here, and we find this. Because this is kind of so keep that figure in your head. Of course, we cannot draw this part yet. We can draw this part, and we can sort of go up to here, and we don't know how far to go. And that's the whole idea right now we're going to try to do. And then we will keep completing this figure. And once we complete the figure, we will see the rest of this. Okay, that's kind of what we're doing right now. So we need to find t hat. T hat is the time at which we jump. This is going to be the t hat. We don't know that yet. Just 1 second, please. Okay. Okay. So we know that if there is no jump between t hat and 3, then lambda 2t is basically this formula from t hat to 3. In that picture, we are now saying that whatever the t hat is, from that t hat to that point, lambda will be this bold line, wherever the t hat is, because the jump happens at t hat, there's no jump after that, so we can just do the slope of half and continue. So this is part 1 of this. Now, the optimal control from 6.67 to 6.8 is 1. That is by Vt at the maximum rate of 1, so long as lambda 2 is bigger than Pt. So 6.67 and 6.8 are these guys, regardless of what happens. The Vt going to be 1. So we'll do that. Also, this will give us y3 bigger than 0, because if we're going to buy, then y3 is going to be bigger than 0. So 6.75 holds. Now I'm going to, just a second, I'm going to minimize this. So 6.75 holds. Because y3 is bigger than 0 and gamma is 0. So we are okay here. Gamma equal to 0. So this is the complementary slackness condition. So that holds. The time t hat of the last jump before the terminal time, let's find this. Clearly, this value will not be larger than at time lambda 2t equal to pt. What we are now saying is that this jump will not be larger than 1.8, where this has become 0. It will not be here. Okay. So where would it be? It'll be somewhere at 1.8 or less. So t hat is going to be, this is basically that line that runs equal to the price trajectory. And when it runs to price trajectory, you can compute that t, and that t is 1.8. You can look at that figure. It's easy to see it's 1.8. Since pt is decreasing at the start of the problem, why is plural? See, there are always some little typos that somehow gets in there, because these days the book publishers don't do copy editing. They don't have the time. and you have to do all your editing yourself. And in a 600-page book, something happens. So this should be just singular. I will check the book later, and one day I will send all little corrections. This is not going to be a 5th edition. It'll just be a new printing, but it may be another 6 months or so before I send everything back to them. So this is the start of the problem. PT is decreasing, and it appears that selling at the maximum rate of 1 should be optimal. Because I'm selling, then I can buy at a lower rate. So I can start selling at the beginning. Since the beginning of inventory is y0 equal to 1, sell can only happen up to t equal to 1. Because after t equal to 1, y becomes 0, and I'm not allowed to short sell. So I enter the constraint y equal to 0. And when I enter that constraint y equal to 0, that's where the jump happens. So y1 becomes 0. And suppose that we do nothing after this in the interval 1 to 1.8, then t equal to 1 is an entry time, and t equal to 1.8 is not an entry time, and t hat equal to 1. Hence, according to the maximum principle, 4.29, if you can go back, lambda 2t is continuous at t equal to 1.8, and therefore lambda 2t is given by 6.76 from 1 to 3. So we have extended this guy. We have now got that t hat to be 1. So what we have done in the figure is that we have gone all the way. We knew that we're going to go to somewhere here, but we did not know whether it's going to be this. We know it's going to be less than 1.8. But now what we did is we start from here because we're going to combine these two ideas to find what's going on. So what we did is we start here. We know that we have 1 unit of wheat, and if you start selling that 1 unit of wheat, we will be empty by 1. And once we are empty, we cannot do anything because we cannot short sell. We already know we can buy here because of this. So we do nothing here. And now we are selling. When we sell, again, remember lambda 2 is still slope of half. But remember, we are going to be a singular control. No, I mean y equal to 0 here. So we're going to do nothing. And we're going to do nothing means that lambda 2 will become PT at this point. So we can start our lambda 2 from here all the way down to this, again with a slope of half. This way slope of half, that way slope of minus half. And then we can go from here to there. And if we go from there to there, then we know the lambda 2 value here. And we also know lambda 2 value here. So we know the value of the jump. By doing this calculation, we know the value of the jump. So now in the figure, you can see everything is clear. All we have to do is put those together into 4.29 and find this jump, which is zeta t, which is easy to find. As you can see, it's 5 years and 3 years, so that's equal to 2. And so all of these things are here, and let's just not waste time on that one. We will just go through the quick. So we got up to here. Then you can see, you can do lambda equal to 1. Then we have this equation, and then we can find the eta t. Then there's a jump condition at the Hamiltonian in 4.29. The jump condition say the Hamiltonian, because this, remember, h sub t is 0. If h sub t is 0, we know the Hamiltonian is continuous across this point 1 where the jump is taking place. And tau is the time in the Hamiltonian condition in 4.29. Tau is the time at which the constraint becomes active. So tau in our case is equal to t hat, which in our case is equal to 1. So I can write the condition on Hamiltonian 4.29 by this. This is just the exact condition of 4.29 written here. That's the condition from 4.29 with this part. Once we have this part, I have the Hamiltonian somewhere. I can then put the Hamiltonian somewhere. That's my Hamiltonian. So this is the left side of the Hamiltonian. This is the right side of the Hamiltonian. So I put all of those two together. I know lambda equal to 1, so this lambda equal to 1 at one point is not there's no jump. So that term is same on both sides, so that goes away, that goes away. If that goes away and that goes away, then the left hand side is this one, and the right hand side is this one. So we all everything is here. We know the price, we know the lambda, we know the v, we know everything. So we can start substituting those values, like p1 minus p1 plus equal to 5, which is, if you look in the figure, you will see that that's 1 minus, that 1 plus, so p is 5. So that's that equation right there. We know we start 1 plus 0, 1 minus 1. We know the 1 plus is do nothing, so that is 0. 1 minus is selling, so that's minus 1. So it's minus 1 and 0, so we can put those values in there. And we know lambda 1 plus is 3, because lambda 1 plus is on this side, and this is right there equal to 3 on this side. On this side is what we want to find out. We want to find out lambda 1 minus, because we want to start. We are here up to here. We want to find out how to go from here to there. So we need to have some value here to be able to go there. And that value then is going to be this one. So you can sort of see we do all of this, and then that gives us lambda 1 minus equal to lambda 2 1 minus equal to 5. So when you put all these together, it gives you this value. It gives you this value. And once you this value, we can do the differential equation all the way up to here. So all of these things are done. And once you have that, you have the jump condition. You can find out the value of the jump, which is zeta 1. Zeta 1 is 2. And so all of that works out. And everything is done in figure. So any question here? Because I'm going to now go and show you. I'll do another constraint. There will be another state constraint. And then we're going to have 2 jumps. And somehow or the other, we're going to put all those together, and I'll show you how we get the horizons. Okay. So what are the horizons? In many dynamic problems, by the way, I have worked on the field of horizons a whole lot, and maybe published more than 20 papers on the topic. And this is just a small part of it, but it is something that I'm actually, as I speak, I'm writing. Whatever I'm presenting right now, I'm writing in a short paper that at least I was asked to do it for a conference in France, but I may not have the time to finish it in deadline because don't have a secretary right now, and I never know how to type math. And I haven't learned that yet. So in some dynamic problems, it's possible to show that the optimal decision during an initial time is either partially or wholly independent of the data from some point on, which means that I can make an initial decision without knowing the forecast beyond a certain point in time. And the idea is that you don't know the forecast long time in future. So is it a possibility for me to argue that I can make an optimal decision even though I don't know the data beyond some point in time? The idea comes because the forecast in the near future is more reliable and in a distant future is not reliable. So if I can do a deterministic forecast in the near future, which is also an assumption, but suppose I can do that, and I know nothing about what happens beyond that, can I still make an optimal decision in the beginning? Okay, and how much of the beginning I can make an optimal decision is called that decision horizon. And the time beyond which I don't need anything is called a forecast horizon. If I need nothing, then I call it strong forecast horizon. If I need something, some qualification or something, it's called a weak forecast horizon. But I'm only, I'm going to not going to go all of these into it, but that's the idea. And then if the forecast, even in the near horizon, is stochastic, which is really realistic, then all of these concepts that I'm saying has been extended to stochastic problems in a paper which is a seminal paper by Bess and Sethi in Math of Operations Research. This field of forecast horizon is not, it's now an old field in the sense that you don't see so much work going on in this area, although occasionally you see papers. But it is used, is there, in what is called rolling horizon decision making. And there's another paper. One of my paper on rolling horizon decision making is probably a more popular paper in SSRN, but it's a paper that has been read by, as far as I know, only 3 people. Me and my co-author and the 2 or 3 referees. Just my inside joke. Okay. So the forecast of the future data needs to be made only as far as the time to make optimal decision initial time interval. The initial time interval is called decision horizon, and the time up to which the data is required to make the decision is called the forecast horizon. If the optimal decision during the decision horizon is completely independent of the data beyond the forecast horizon, then the latter is called a strong forecast horizon. If I need some restrictions on the data beyond that, then I will call it a weak forecast horizon. Okay, so this is sort of a little introduction to the definition of horizons. But you can go to Bess and Sethi, IMOR, that you can get more details. I will now demonstrate that t equal to 1 in our problem here, this, and the forecast is only up to here. I know the price is going to decrease, and let's say this is reliable. Let's say the forecast up to time 1 is totally reliable, although that may not be true, but we are going to assume that in this one, because I'm not going to give you a stochastic extension of this problem. So this is that. And I'm telling you the forecast after 1, I don't really care to some extent. I'll tell you what I mean by that, but I don't care so much. So I'm going to now tell you that if I'm going to change this forecast in many different ways, this decision of selling between 0 and 1 is still optimal. That means I can do many things on this price from 1 to 3, and I will have a different decision when I do that here. But that one will not change. So willy-nilly, I can sell the wheat no matter what happens to the price beyond this point. No matter means it's a weak forecast horizon, some restriction. Okay, so I will show you what that is. So in this paper, we introduced the concept of price shield. This, by the way, was never written up before in a paper, but somewhere later on, I think I may have written it somewhere. But price shield says that as long as the new price trajectory in the interval 1 to 3, which means this interval that we are talking about, 1 to 3, as long as the new price in that interval stays below the price shield, I will give you the price shield, then the optimal solution interval 0, 1 remains unchanged and can be a decision horizon. And a weak because I will give you a price shield. So here's the picture. If I extend this lambda 2 trajectory all the way like this, then this is my price shield. And the concept of price shield says that if I change the forecast from 1 to 3, as long as this price remains below the price shield, that decision will not change. Decision from 0 to 1 will not change. So this is called decision horizon, and this is called weak forecast horizon. Now, let us now resolve the problem from 0 to 3 with the new price. This is the new price. Same up to 1, and then it's this. It is not this. It is this. Well, then what happens is I already know what that point is. So far, that point hasn't changed. It may change. but I will tell you a little bit more about that. But in this case, in this price shield, suppose I begin here. If I begin here, I will do this, just like I did before. And when I do this, I will buy, because this is the buy region and this is the sell region. Okay. And so my decision will change. The decision here was do nothing and buy. This was still sell. The decision here now is still sell, but there's do nothing. But then there's buy and then there's sell. The do nothing is that intersection. That intersection may not be this point, because this point is this forecast. This point is some curve, which may have another point somewhere. But whatever that point is, we can find out. And we do nothing until that point. And then we have a price that's like this, and I buy and I sell. Now, the reason I'm a little bit telling you why this picture may not be the picture if I change the forecast, although this will still be optimal. And the reason I'm saying is that if as long as this buy is, so see the argument here, as long as, okay, so this can be concluded, we can conclude that, provided the buy interval is not shorter than the sell interval. So the reason is that if buy interval is shorter than the sell interval, then I don't have enough wheat to sell, because I cannot short sell. So I may need to do another little buy sell. Right now, if it is shorter than that, now if buy interval is not shorter than sell interval, then then what happens is I will buy more, sell less. I will end up with a positive wheat inventory here. But remember, the price is increasing. At that point, the price is higher than the price that I bought. I'm buying at this price, and I keep the wheat at this point. This is going to be higher than that price, so my wealth is not bad. I have some positive inventory at this point. But if this interval is less than that interval, then I ended up buying less and selling more, and that's not possible. Then this is what you have to do. If not, the optimal control inventory will need to be revised. Lambda 2 may have another jump to not violate the short selling constraint, which is kind of similar to this situation that we happened. Remember, we sell and then we do nothing and then we buy, and there was a jump. So there may be another jump somewhere here, which we can, if I have another price forecast where that happens, I resolve the problem here again. And I can do that because I know how to do it. I know how to do all of this now. But that's not going to change. So far, this gives you an idea of a price shield and a weak forecast horizon. Any questions so far? Because I'm going to go to the next one where I actually give you a strong forecast horizon. Okay. So what I'm going to now do is do a strong forecast horizon. And the short forecast horizon, strong forecast horizon comes. For that, I'm going to introduce another constraint called the warehouse constraint. That means I'm, as a buyer and seller of wheat, has a silo or the warehouse in which I can only hold 1 unit of wheat. Whatever that is. It could be 100 kilogram, could be 100 million kilogram. I can only hold 1 unit of wheat. So I have to have a constraint called 1 minus y bigger than or equal to 0. And I need to put that constraint into this problem, which is not there yet. This problem. So I need to put y less than 1 here as well. And then if I put y less than 1, I would have to have another eta in my Lagrange multiplier, right? I need to have another eta 1 or whatever you call it. I will have to have that. Okay, so I'm going to do that. So first the Hamiltonian. I now changed, let me see, what did I do? I changed the time from 3 to 4. And I didn't tell you that on this slide. Oh, it's right here, t equal to 4. So the price is now same up to this, but then it is, it's instead of 2 to 3, it is 3 to 4. 2 to 4. So I increased the time interval for the problem. And bang control is from the Hamiltonian. It's now has one more branch. That means if I am at 1, then I also have to put -1, because if I'm at 1, then I cannot buy anymore. I can sell, but I cannot buy because my warehouse is full. It's a hard constraint. I cannot buy. Okay, I don't have another place to store. Remember in the first problem where this warehouse constraint was not there, I have unbounded capacity to store. I have an infinitely large warehouse. So I don't need to worry about, I can just keep buying as long as buying is good, and I don't care about how much I buy. Okay. But here I have to worry about that. So I have 3 different banks. One for short selling. This is for short selling. This is for not able to buy when warehouse is full. And this is our regular bank, which is for the beginning problem of Ejiri and Thompson, because they didn't have this constraint. So now I have eta 1 times minus v. And so I'm not going to go through all of that because we know everything. I'm just going to hit the major points here. Now we have gamma 1 and gamma 2 because we have constraints. So now we have lambda 4 minus is P4 plus gamma 1 minus gamma 2. Use again the principle, maximum principle in 4.29. And now I'm going to have this complementary slackness condition. Okay. Because we have 2 constraints, y bigger than 0 and 1 minus y bigger than 0. So we got these guys right. And then we are going to start a guess. That was gamma equal to 0. Now I'm going to start gamma 1 and gamma 2 equal to 0. And then just like before, lambda 2 is going to be like this up to 4 from some point t hat. And again, we can find the trajectory intersection. We again find out that t hat is going to be bigger than these and all of that stuff. So I'm going to now go, because there are lots and lots of equations that needs to be solved. Like here, you see it's all going like this. But let's go to the picture. So we start from this point where lambda is equal to price. Lambda 2 is equal to price. And we go like this with half. And if we go all the way like before, we hit this price trajectory. That's 8 by 5. We know that the jump is going to now happen because now remember the trajectory is not, it's a different price trajectory than before. So the jump is going to happen somewhere after 8 by 5. And that is a little bit more complicated now because this was easy. This jump was easy. So I'm not going to explain this jump anymore. Because once we are here all the way up to there, and then we come back to there. So this from this point on, although this point is 17 by 6, not 3 in the previous problem, but from this point on, the problem looks very similar to the last section, except the time is 17 by 6, not 3. So from this point on, we just go like this, all the way here, then come back here, got this jump. And then depending on where the lambda is comes to price, we will have a buy, do nothing, sell. That was not different from the previous in some sense. Okay, but we need to do this. We need to find this jump, which means we need to find this point. That point is still far from this point, so we still need to figure out what to do here. So let's go. also stays above the price trajectory interval 854, so that if there were no warehousing constraint, 6.82, which is a warehousing constraint, the optimal in this interval will be to buy at the maximum rate. What we are trying to say is that if there was no warehousing constraint, I will go all the way from here to there and I will buy. That means I will sell, do nothing up to 8.5, and I will buy. So I don't have this, I have this thing all the way up to here, and then there will be a jump. There will be nothing here, all the way to do nothing here. So this will be do nothing, but I will buy all the way here. And this will be lower than that. So I will not do anything. And then the jump will be like this. So I go here and jump will be like this. But I cannot buy because my warehouse will be full. If I buy all the way from to here, you will see I will have 8.5, 2 to 4 already be 2 bushels. And there will be more than 2. And my warehouse is only 1. So I can only buy 1 unit of wheat. Right? So let's see how this thing works out. If I can only buy 1 unit, I'm already up to here, right? I'm all the way up to here, and I don't know where I will have a jump. So I want to find out where the jump would be. So what do I do is the following. Since my warehouse is 1 unit, and buying happens when the lambda 2 trajectory is above the price trajectory. I think here reading the book is good, but I think here the lecture gives you a little bit better idea of what's going on. You cannot explain everything. You need like another 5 pages in the book if you want to transcribe everything that I'm saying right now, and that's not practical in the books. So what I'm trying to do now is that I can only buy 1 unit of wheat as long as I am above the price trajectory. So what do? I know that my slope of lambda 2 is going to be half, and I am going to have some jump here. So I'm going to kind of go from somewhere here to somewhere there with a slope of half. And when I do slope of half, I will have part of it is above the price trajectory in which I'm going to buy, and that part cannot exceed 1 unit. Because if you start buying somewhere and stop buying somewhere, that time between here and here has to be equal to 1 unit. Which means I'm going to fit a line of slope half. I can sort of go parallel like this. I can put this line above. In this case, the line begins here, like that. And if I do that, I will see that point and that point is more than 1. Or I can begin the line here and go like this. Then I will see that the intersection from here to here is less than 1 unit, which is okay, is feasible. I can buy 3/4 of a unit. But why shouldn't I buy the whole unit? Because price is increasing. Price is increasing. It's good for me to have lots of wheat here. And the lots of wheat in this case means 1. That's all I can do. So they will be doing nothing after that because I cannot buy all the way from here to here. So there has to be a reason of buying and a reason of doing nothing. And if I have a reason of buying, a reason of doing nothing, then the reason of buying has to be 1 unit apart. And that's it. That solves our problem. I like to fit this line so that its intersection with the price trajectory is exactly 1 unit apart. And if you do the mathematics, you will see that that point is 11/6 and that point is 17/6. The difference between 17/6 and 11/6 is exactly 6 divided by 6, which is exactly equal to 1. So you won't do this in a book. It never says 6/6 in a book. Okay. So once I have this, the rest I know exactly what to do. So this picture is done. Now I just go to show you what I need to do. So we are here. Then we just go and find out this lambda 2, find the t hat, which is the 2 time units. See, this is 17.6, and that's equal to t hat plus 1. This is the price trajectory on this side. This is the price trajectory on this side. So here, so this is the, so we are trying to find t hat. So t hat is this point. Okay, so the price here is t hat plus 1, because t plus 1 is the price forecast here. So this is the price on this side. This is the price on this side, right there, that one, that point. This is the price on this side. This is the price right there. And that one says I have to go from here by a slope of half to here. So that is the slope of half. So that's up to that is the price minus 2t minus 1 plus 7. So that's the price at t hat. That's the price at t hat. And I have to go by a slope of half for one time, because that's going to be half. So what I'm trying to say is that from here to here, the lambda 2 is going to go increase by 1/2. So I'm going to add 1/2 to this point to get here. So I'm going to add 1/2 to this point, and I say once I do that, I should come here. So I have an equation in t hat. That equation gives me t hat equal to 17/6. And then everything's good. Gamma 1, gamma 2 is 0. The guess is correct. I'm done. So I actually now have solved the problem. And the only thing need to do is to find all the mu's and lambdas and etas and gammas, and all of that can be done. That's just equation, go around and use different equations and get there. So now, here's what I'm now to say. We're doing good time-wise. So what I'm trying to now say is that this 17.6 is a strong forecast horizon, and this one is a strong decision horizon. What I'm now trying to say is the following. I don't need the price shield anymore. When I say strong forecast horizon, I don't need the price shield. Although I put it here, I don't need it. What I'm now trying to say is that if you change the price from 17.6 on, like means price in this interval, whichever way you want, I don't really care. That solution of selling from 0 to 1 will not change. That means if somebody told you that the price is going to be this price all the way up to here, and after that, I don't know what the price is going to be, then you'll say, okay, if you don't give me the price, I don't know how to formulate the optimal control problem, and I cannot tell you what the decision will be here. What I'm trying to tell you is that if this was a strong forecast horizon, then you can put any price forecast you want here, and then use the control theory to solve the problem, and you will see that this decision will be sell. This is a main important idea here. And so that's, I'm going to demonstrate you by 2 examples. I'm going to change this price in 2 markedly different ways and resolve the problem and show you that nothing will change from 0 to 1. That decision will be sell regardless. That means in this kind of situation, if the price goes from here to here, and then whatever happens here, I can simply start selling my wheat and empty the warehouse at 1. If things happen here, I can do things here to take advantage of those price scenarios and increase my profit. But there's nothing I can do here more than what I did to increase my profit, which means that it will not be okay for me to not sell. Suppose the price here went to 5,000 at this point. Suppose the price went like this, 5,000. You will argue that if the price went 5,000, I should not sell, because I should keep this wheat, because in the end, it's going to increase to 5,000. My argument to you would be that you can always get that 1 unit of wheat here. So there's no reason to make not money. Just make this money here by selling, and then you have the empty warehouse, and the empty warehouse will allow you to sell, fill up your warehouse again at a lower price. That means you sell this. If you didn't sell this, you cannot buy here because your warehouse is only 1 unit. So regardless of what you do, that scenario says I can always fill up my warehouse, and so there's no reason for me to not empty it right now, and I can and make more money by filling the warehouse later, and so just go ahead and do it. This is the central idea that's going on here, that says that if I have constraints like not short selling and warehouse, these constraints somehow straitjacket me in a way that allows me to make a decision already. Not, this is my nature. I have constraints. There's nothing I can do about it. And with those constraints, I cannot make use of everything that happens in the future. Because with those constraints, I can make use of those constraints before, and then again make use of it later. But if it's totally unconstrained, then it is possible that I will just keep this wheat forever. But once again, remember, there's also a question of cost. If I keep this wheat for more than 2 units, I also cost money. But if it's okay to cost money, $0.50 per unit time, it will only cost me $2. But if I have $2 cost of that and price went up to 5,000, I will still keep it because my warehouse can hold more than 1 unit. I can have 1 year and 1 year, and I can have 2, and the 2 at 5,000, the price will be $10,000. Why not? Okay, so let's now show you 2 price trajectories, 2 scenarios. Here's one scenario. I decided to increase the price from 17.6 to all the way up to here, which is almost my 5,000. Okay, so I increased the price to 8. Notice my price shield is only 6.5. I have now increased the price beyond the price shield all the way to 8. Right. What do I do now? I resolve the problem. I resolve the problem. I still do sell, do nothing, buy, and do nothing. So all of that decision is good. In fact, in this case, even this decision is good. So if I were to have something else, I might even increase my decision horizon to here and call some weak forecast horizon here. I don't know. I have to do those calculations, but it could have been done. But right now, my idea is to demonstrate only that this is a strong forecast horizon. This is a decision horizon. So I don't want to go beyond that right now. So this is one. Now let's see what happens if I do something else. Now suppose I change the price to this. From 17.6, I decrease the price. If I decrease the price, clearly this buying and then holding the wheat for this amount of time is probably not a good idea. So let's see what I do. If I do this, you can see what I'm doing now. I go here, and then you see I draw a picture here of this line so that whatever I buy here, I will sell here. So you see that I will put the line here so that this interval from here to here is equal to this interval from here to here, which means whatever I buy here, I can sell, because there's no reason for me to keep the wheat because price is going down. I want to get rid of the wheat when the price is still higher than this price. So my optimal control, again, I can do this. Then there's a jump up. I need to find out how much of the jump up is. That you do by fitting a line of slope half in the price trajectory so that the price trajectory below the line and the price trajectory above the line are equal portion. So whatever I buy, I sell. So I buy at a lower price, I sell at a higher price. But if I buy exactly this amount, sell this amount, then I'm done. Remember, the rate of buying is 1, the rate of selling is 1, so they have to be equal. If the rate of selling is half the rate of buying, then the different calculation has to be made. That means that if the selling can be faster than buying, let's say twice faster than buying, then you can actually buy more and then sell in half the amount of time. So this line will move a little bit up so that this portion will be 2 times this portion. So you can see by having this picture, I can solve almost every problem by this intuition. And once I do that, I can do all the etas and gammas and whatever the variables there are. So I go like this, come back here. This is still selling. I'm still selling here. This is different, value different. That value is still the same. That value is different. Amount of jump has changed. So what I'm trying to say is that at some point around I have written that there should be a paper of sources of horizons. I've never done that paper. I don't know how to do it because there are just many sources. But I have written somewhere that one of the sources of horizon is the jump. See, what happens is because there's a jump, I have a lot of room for this point to maneuver. So I can keep this trajectory here by simply increasing and decreasing this jump. This can start here, this can start here, this can start here, this can start here. That jump allows me to do many things here without affecting this. So the jump in adjoint variable is a source of forecast horizon. But it requires a more rigorous study of what that is. And there are other sources. There's a constraint on warehouse is a source. Short selling is a source. But those are equal to the constraint jumps because these are state constraints. So it gives you a jump. There's a paper of mine that says the fixed cost in inventory problem where you have to have like a lot size model. The fixed cost also gives you horizons. And that idea came all the way from Modigliani and Hone. And Modigliani was one of the Nobel Prize winner. And if you, did everybody got my SS policy survey? Did somebody send that to you? Hello?
I don't think so. No.
Oh, okay. So I have written a survey that's coming in production and operations management. The survey is like 60 pages long, and it's a survey on SS policy when there's a fixed cost of inventory. And if there's a fixed cost of inventory, the policy is SS. That comes from way back when. But Modigliani and Hone actually wrote a paper, and Wagner Wittner wrote a paper in 60s that started the idea of the horizons. And in my other paper that I wrote that's also coming in production operations management is the paper on contribution of the Nobel laureates. Is that paper come to you? No. So
Yeah,
it is time for me.
that one did come to us, yeah.
What did you say?
Yeah, that one did come to us. The one that
So
you were
if you,
writing. Yeah.
okay.
Yeah.
If you look at that paper, you will see there's a row on my table which is called decision and forecast horizon, and you will see the first few papers are Modigliani, Hone, and these kind of papers. And then you will see another column where I give you the application papers. You will probably see some of my papers there. And so that paper is also forthcoming, and now it is an SSRN. So if you don't have the final version of it, you can go to SSRN and look at that. Although I am still revising that paper a little bit as I get comments from different people. And so by the time the paper comes out in print, it may have another 1 or 2% revision. I mean, the paper is more or less done. It's only when I find more things, I like to complete it, and I'll do that. Okay, so you can see this idea is rather powerful, and we have now found that we got the horizon of for strong forecast horizon. There's a note here that says that you can actually solve the problem by t equal to 17.6. And the question now is, the idea of forecast horizon is this. If this is a forecast horizon, then anything about this is also a forecast horizon. Because obviously, if I can change the price trajectory from here, I can also change the price trajectory from this point on, and that's also forecast horizon. So if there's a forecast horizon t, then any other t is also forecast horizon if it's bigger than the previous t. So then there's the idea in the literature, what is the minimal forecast horizon? If there are a lot of forecast horizon about this, then is there a constant of minimum forecast horizon? I'm trying to say here is that possibly 17.6 is the minimal forecast horizon. But that's something I'm not putting those concepts in this book, but that's all I'm saying. So I think that we actually cover. If you have any question right now, I'm going to switch to chapter 7 after we come back. So I'm going to take a break of 5 minutes, and then we'll come back to chapter 7. And also, if we cover a lot of material, there is some possibility that on 28th of April, we may even skip a class. But I don't know that. And I prefer to do it. I prefer to do the class. But if I am if it's not feasible for me or not practical given the schedule in Israel, I will let you know. There is also something that I will mention, but I will not say that you need to do it because the time is inconvenient. I will give a talk on differential games and supply chain coordination, which I think I would probably like to cover that in this book later on towards the end when I do stochastic differential games. But I'm literally giving the same lecture in Israel at the school called Bar Ilan University. And that lecture will begin at 12:30 on the same day, Thursday. So I have that lecture and then the class. But that 12:30 to 1:30 would be that lecture. And if anybody wants to listen to that lecture, you have to wake up at 5:30 in the morning. It takes us time. But if you want to do that, I will be happy to ask the Israeli people to send you a link. Okay, so that's that. Okay, I'll see you in a few minutes. Hello, everyone. Is
Hi,
everyone there?
Yeah.
Hi, Professor.
Can you see my screen?
Professor. Yes, Professor.
Yes.
Thank you.
Yes.
Okay. Chapter 7 is application to marketing. And every chapter that I have in the book has some reason of some techniques that I want to bring in. So chapter 6 was gave you the idea of distant forecast horizon and also applied the constraints. Chapter 4, we also had an idea of turnpike horizons in chapter 6. We also had a okay. Chapter 7 has several new concepts, and one of them is solving the problem using what is called the Green's theorem. Green's theorem is something that we learned in calculus first year courses, and it turns out that there are some cases Green's theorem gives you a very quick way of solving the problem, and it it solves the optimal control problem without actually maximum principle. And so we'll talk about that later. And we'll also have some other ideas of chattering control and things like that. So we'll so in the marketing problem, the state equation is rate of sales expressed in terms of advertising, which is a control variable. It's a question of how to advertise. What is the advertising schedule that allows you to increase your sales in a way that maximizes your profit? The control constraint is natural. Advertising rate has to be non-negative. It cannot be negative. No such thing as negative advertising in any case. I mean, negative advertising. There's negative advertising, but there's no case where advertising rate can be negative because it's the amount of money that you use for advertising. The earliest model that we know of advertising is a well-known model of Narlow and Arrow. Both are economists, and Arrow, as you know, was one of the top economists of our time. He got his Nobel Prize for general equilibrium theory, and he died recently, about maybe a year and a half ago or so. And I had a lot of connections with him, for the last 10 years or so. And I have also written 2 papers with him. I also recently, I think, wrote a laudatio for him too. So anyway, he these 2 guys developed this model, and they were economists, and they considered advertisement as an investment in building some sort of advertising capital, which we normally call goodwill. Goodwill is a, if you if you were active in learning about what was happening in U.S. politics in the last 4 or 5 years, you knew that the Trump was selling called Trump brand, and he was making money by brand name. Put his name on a hotel, and a hotel will pay him some money, and that's called goodwill. In some sense, goodwill is treated as a capital on accounting books. So let GT denote the stock of goodwill at time t. It's an asset, so you can call it a stock of goodwill at time t. And the goodwill is an asset, so it depreciates over time if you don't do anything about it. So that depreciation rate is delta, so it's G dot is minus delta G. But you can also increase the goodwill by amount of advertising, and so you put U, which is the advertising. So the advertising increases the goodwill, and it decreases over time because of the decay. And so this is the equation with the initial value of goodwill that you have in some way or another. It's not always clear how you measure goodwill, but accounting people have figured out some way of doing it, and they usually measure it in dollars, and then they have it on their books called asset. When you look at asset and liabilities of an accounting statement of a company, you will see asset and listed capital and equipment, goodwill, and whatever. Okay. To formulate the optimal control problem of a monopolistic firm, which means there's no competition, I need to come with the rate of sales. And the rate of sales depend on price, goodwill, and some external factors, weather, temperature. If the temperature is high, you sell more Coca-Cola. If the temperature is low, you don't. So those are some external factors that you don't have control over, but they can affect your sales. The rate of total production cost is C of S, where S is the sale. So we can write the revenue as the revenue, which is P times the sale, P is the price, minus the cost of sale. So the revenue is a function of P, G, and a Z. And the cost of advertising is U. So the profit is R minus U. Remember, this already takes into the account the cost. So this R is not quite revenue like this revenue. It already takes into account the cost of sales, but it is the revenue net of advertising cost, not net of C. And there's a discount rate because we always put discount rate when there's an infinite horizon, and we integrate to make a profit here. And we are maximizing with two control variables. One is U, one is P. So U bigger than 0, P bigger than 0. Now, this is a concept that appears in a optimal control problem. If I have a control variable, which is P, which does not appear in the dynamics, then that control variable can be maximized outside the optimal control problem. And to do that, I just take the derivative, because since there's no dynamics to P, I can maximize R for each point in time, and then I can maximize the R, which is the rate. I can maximize inside the integral because I can use the max of R. So I maximize R by taking the derivative with respect to P. Whichever way I want to maximize with respect to P, you can. But one way to do it is to take the derivative with respect to set it equal to 0, first order condition. Then when you solve this equation, it'll be a function of G and a Z. So at any time, price, whenever you know G and a Z, you can set that price. And this is aside. This is just some economics in there. We are done. As far as the control theory is concerned, you can put this P in there. So you put P star of G of Z. Then the revenue function is just a function of G and a Z. And the price is out. It's no longer so we can remove this P from here. Only our control problem now is in terms of advertising. And since we already maximized the price point-wise, at every instant you maximize the price, and the instantaneous optimal price is P star of T. So we can
Excuse me.
Just a second. If you want to solve the problem, then from here we can go here. From here we can go to here. Sorry, from here, then you substitute p star. We can go to here. So this is pi of z, and if z is constant, then we can even remove z from it, and this is the optimal control problem that Narlow and Arrow solve. So pi is only a function of goodwill, which is the profit, a net of advertising, and then you put g dot is u minus delta g equal to 0. You have a control problem. So I'm going back to here. There's a little bit of economics here, and there's a question. What is the question?
Could you explain why that line's under equation 7.5 says which implicitly gives the optimal price P star equal to P depends on G and Z?
Okay, but this is something you should know from from the elementary algebra or whatever. If I maximize this with respect to P, then the maximum P will depend on whatever is other arguments there are.
Oh, okay. I got it.
Okay, so the P will only be a function of G and Z because P itself is being decided. So P cannot be a function of P. It can only be a function of all the other things that are there.
Okay, thank you.
So that P will then just be a function of G and Z because G and Z are time dependent. We don't put T here, but we put T here so that this is T and this is T and this is T. So P star T, once I know GT and I know ZT, I can find P star T. If I have a P star T, then I can put P star T right here, right? So that P star T is also a function of G and Z. So this whole function is only a function of G and Z now, right?
Yeah.
And that's what I call this to be G and Z.
Yeah, so it's not followed from the equation 7.5.
Sure, it follows from equation. It follows from this equation.
Okay.
Because when you derivative of P, there's an equation which is solved in terms of P. See, this equation has one variable called P.
Yeah.
So P will be equal to, if you solve this equation, then P is equal to this.
Yeah.
And that is all a function of, because remember sale is PZZ, right? So there is a sale here, right? But that also has a P in there, right? So
yeah.
so in some sense, everything here is a function of P and a Z, G and a Z. And so when you solve it for P, it'll be only a function of G and Z. It follows from 7.5.
Okay. Yeah. Thank you.
But this is a little bit economics, and I just put it there. It's not necessary. But because if you think about this P star, the S is also a function of P. So this equation has a P on both sides in some sense, right? But somehow they write it in some sense because you define an eta. And eta is the elasticity of demand with respect to price. So once you define eta, then you can just say P star equal to this. Okay? The assumption here is that the eta doesn't depend on price. So when you do this, it doesn't depend. So this is they call elasticity of demand. It is defined this way. And this formula also has a name for people who first decided this formula. And there's a book by Cohen and Syed where they say that marginal revenue is, so if you take eta minus 1 on this side and eta on this side, it becomes eta minus 1 times P divided by eta. And you can show that that's equal to, that's the marginal revenue. So that's derivative R with respect to P, okay? So that's marginal revenue. And that C prime S, which on this side is marginal cost. So this equation really is the the fundamental equation in economics called profit is maximized when marginal revenue equal to marginal cost. It's just the first order condition of economics. And I cite this book because this book has this formula, and I also know both of these guys. He was the dean of Carnegie Mellon Business School when I was a student, and Cohen was my first year supervisor as a PhD student, and I wrote a finance paper as a first summer paper because Cohen was a finance professor. And so I wrote that paper, and that was published in Journal of Financial and Quantitative Analysis. Carnegie Mellon, you had to write a summer paper the first summer as a PhD student, and they insisted that that's a publishable quality paper. But it doesn't mean it will get published, but it should be publishable quality, and mine was actually published eventually. So I suppose it was a publishable quality. Okay, so, and then, I don't know, I just said little things about this. Coleman Cohen, when I interviewed Duke, after my Rice University job, the Duke offered me, after my Rice University job, it was only 1 year after my PhD. And 1 year after my PhD, the Duke offered me associate professor position. So I would be associate professor in Duke in 1973. And there I talked to him, and I told him Cohen was my advisor. And so they actually were looking for a finance professor. So they hired Cohen, and Cohen went to Duke University as a professor, perhaps because of me, because I let them know what was going on. But anyway, I did not join Duke. I went to Toronto. So I do not know what life would have been mine like if I was a professor at Duke at 73. That's something one can reminisce on. Okay, so pi gz minus u integrate u bigger than 0 is our objective function, and this is our state. So this is the problem that we are now working on. Just forget about all those things. Now, I didn't mean forget about it, but this is not concern to us anymore in the optimal control book. It is just some side remark. It's reasonable to assume that this is increasing in concave, which is marginal utility is diminishing. It's a more of a standard assumption in economics, which means the pi prime g is bigger than 0 and pi double prime g is less than 0, which also means that we have a concave maximizing problem, which also means that the necessary conditions also become sufficient. So these are all very nice and handy tricks that you need to learn when you publish papers, and this is one of them. Because everybody will say, okay, you got necessary condition, what about sufficiency? So you say, okay, I assume this. Why are you assuming this? Well, this is the standard assumption in economics. Okay, so we do the Hamiltonian, we do lambda dot, we have a sufficiency condition of transversality condition, which is not necessary, I mentioned to you many times. And the adjoint variable lambda t, we already know, is the shadow price associated with the goodwill. That means if you give me a little bit of goodwill, what is its value? Okay, and that's decided by the shadow price. And because of that value, as I talked to you about why maximizing Hamiltonian is at each point in time decouples the problem from present to the future, is because of that, because of that shadow price idea. The current net profit is pi g minus u, and there is an indirect net profit, which is lambda times g dot. Lambda is the price of g dot, so that is the price of goodwill. That is the value of capital gain created by our advertising. So if you see the Hamiltonian, the first term is pi g minus u, which is the current profit, and the second term is the capital gain that you acquire by investing by u. So if you factor in the capital gain along with the profit, then the capital gain takes into account all the future things that will appear because of this u. And if you include that along with the current profit, then h becomes some kind of a profit which somehow takes into account the future. And so you can then maximize the Hamiltonian at each point in time without worrying about the future, because lambda already captures the future. That's sort of the idea, which is a main idea of economic idea in optimal control theory. And we talked about that in general setting in chapter 2, but it will come again and again. But when it comes again and again, it has more teeth to it. You can see the names of what is going on. It's not abstract anymore. We can also find the long-run stationary equilibrium, which was defined in 3.108. There are no constraints, so we can do a triple rather than a quadruple, and that gives us G bar given by this idea here. And you can see that we will have to assume pi prime 0 bigger than 0, and this is less than that, because if you assume this, then there is a unique solution for G bar, which is positive and bigger than 0. And so we have a Goodwill, which is long-run stationary equilibrium. Notice if this is not satisfied, then this company should not be in business, because G bar will be less than 0 or equal to 0, and there is no reason for this company to be in business. So that's that. And so there's another little bit of economics. If you look at this condition is interpreted by a man named Jackman in a paper that I cited somewhere earlier, I think, this one right here. That paper is never published, so I still keep him because this is the paper that I read when I was a student. So there's elasticity of demand with respect to Goodwill. And this equation can be then written by using this formula, can be written this way. Once again, this is economics, not control theory. And this is the optimal. So the property of G bar, and now is an important idea that comes in control theory. It said that G bar is that the optimal policy is to go to G bar as fast as possible. See the idea, as fast as possible. So this idea, I will make some comments because it is something that I've done a lot of work with. But this idea also has an important concept, which is the following, which says that see what G bar is. Look at your control. Your control is given by, where is the U star somewhere, the formula there? Yeah, your control is along this line. Your control is given by delta G bar. It's a singular control. It's given by delta G bar because once you are at G bar, you want to maintain G bar. If you want to maintain G bar, then you want to maintain G bar, then this G dot becomes 0 at G bar, and this becomes G bar, so U becomes delta G bar. When U equals delta G bar, if you put U here, which is delta G bar, then you can see this is U bar, and this U bar and delta can come here as 1 divided by delta. So you can sort of see that, delta can come on this side. So this is a constant. And you see U bar divided by PS is a constant. And that means that in equilibrium, the advertising is a constant fraction of sales. This is sales. This is sales in dollars, P times S. And U bar divided by PS is given by this constant. This delta, the U bar becomes delta G bar. This delta can come on this side. When it comes on this side, this is some constant. And it says that U bar divided by PS is a constant. That means the constant fraction of sales. And I've written somewhere, there is a marketing literature that says that some companies simply use advertising as percent of sales. For example, some company says, we're going to use 1% of our sales into advertising. Every year, we put advertising budget as a percentage of sales. If that is their policy, then this particular condition says that that policy is optimal under whatever conditions that we have. And so it sort of justifies the practical implementations of advertising budget. And because of that, then the idea again in marketing literature, and that is the idea of causality, which has now become quite popular right now in our field because of the recent Nobel Prize given to Engrist and Imbens in causality. And causality is basically saying, is advertising cause sales or sale cause is advertising? Or they cause each other? So that's sort of, you have the data, and from this data, you have to figure out which causes what. But notice, if you look at this equation, you can see the advertising causes goodwill and goodwill causes sales. So advertising is causing sales, because otherwise why would you advertise? But if you look at this equation, then if companies are setting the budget as a percentage of sales, then advertising is caused by sales, right? Because that's how you put the advertising budget. So if you have the data over a time series data for maybe 5 years or 10 years, and you want to do statistical analysis of this time series for causality, the causality may not give you a right answer because the data may be created by this equation 7.12, or it may be created by this equation, or it may be combination of both. So the data has to tell you whether advertising causing sales, or sales is causing advertising, or advertising and sales cause each other. So these are some of the concepts on causality. If you are working on empirical aspects of many of the things that we are going on right now in our field, then these are some of the important issues. And Guiwa, Professor Guiwa Wang, is actually writing papers on these. In fact, recently he had a paper on causality in terms of, I don't know, pandemics or whatever that he's working on. And I worked on causality in 1980s and wrote some papers with data. And there are some of those papers sitting in the literature. I also developed the statistical concept of econometric concept of causality for multivariable problems. And that paper has been used by economists for estimating causality. So anyway, there are some papers listed in my book somewhere that are papers on causality dealing with these kind of issues. So as fast as possible means that if my G0 is less than G bar, then I want to go to G bar as quickly as possible. So if there's no upper bound on control, then it'll be impulse control. I jump straight away to G bar by a high rate of advertising for a very small amount of time, and I put the impulse. We have already defined the impulse in chapter 1, and we will see a little bit more of it now. Or if there's a control upper bound on U star, let's say Q, in which case the fastest rate to jump is to use the advertising Q, which is the maximum advertising I am allowed, and you go to G bar with this rate Q. If G0 is bigger than G bar, then you do nothing. You put U equal to 0 for a while, and you simply decline to G bar, and that's going to give you a fastest rate to go to G bar. If you're already on G bar, you do nothing because you're already on G bar. So the picture looks like this. This is our G bar. If I'm here, I let U star equal to 0 and let goodwill decline to G bar and come here. The reason I don't want this G0 and put control 0, maximum control here to maintain, no, or put UG0 to maintain here, is because maintaining that level of goodwill is very expensive because it's declining and it's very expensive to maintain it there. So you want to maintain it here. On the other hand, if G0 is less, It's not creating goods. This will create more sale, but the cost of maintenance is very high. So there's a trade-off of maintenance. Here, G0 is very little, and so sales are not very high. So I want to build up the goodwill. I can build the goodwill either by, depending on the constraints on control, if there is no upper bound, then I go to impulse and come to G bar here and then go like this. Then set, after I get there, I set the U bar equal to delta G bar, which is a singular control. If I have an upper bound of Q, this is the impulse. Its impulse is defined by G0, G bar, and 0. This is the notation that we introduced in chapter 1. And please go back to it because these are going to be, remember now, all of these are going to be in the final exam. So you want to familiarize with all these concepts. And if there's an upper bound on U, then you can use the highest level of advertising Q, in which case the equation will build the goodwill along this dotted line, and you will come here and you will go along this. There are sometimes in some problems, even the highest rate may not get you there. It may asymptotically go to U bar. It may never go to G bar. But that's also constant of equilibrium. That says that if you cannot reach there, you will asymptotically go there, but you not go there ever, but you will asymptotically approach there. But if you're already there, you stay there. It can also be from above. If the G0 is very high, there may be problems where declining can be asymptotic, but never get there. It's possible. For example, not in this case, but if G bar were to be 0, this G0 will never go to 0. It will asymptotically go to 0, but it will never actually become 0 ever. So this is called fastest approach possible. Now, if there were constraints on control, then sometimes you can have a problem where fastest approach is not optimal. And this idea of fastest approach is so ingrained in turnpike theory and in economics and in marketing that it has a name. It's called MRAP, most rapid approach path. And when I was writing a paper along these lines, I developed these ideas in a more general setting called, I had a paper called Nearest Feasible Approach Path. It was published in Journal of Optimization Theory and Applications. You will see some reference here. And I changed the name MRAP to Nearest Feasible Approach Path because when the control is bounded, this may not be optimal. So I thought I had a great idea, and I changed the name to Nearest Approach Feasible Path, which is more like NAFP instead of MRAP. And this was one of the biggest mistakes I made in naming. I have succeeded in some other things, like forecast horizon is termed by me. It used to be called planning horizon, and now the literature call it a forecast horizon. So I was succeeded there. But here I did not succeed. The literature continues to follow MRAP regardless of this idea. And not only that, my paper was almost never read or picked up by other people because they were also searching for MRAP, they did not know what NFS means. And in that paper, I developed a concept called some kind of indifference point, which eventually got named by Skiba point, by a man named Skiba in Russia. And a lot of people then wrote on Skiba point. And only people found out later that my paper, Nearest Feasible Path paper, is actually 2 years or 1 year before Skiba. So it should actually be called SETI point and not Skiba point. But now some people are now calling it a SETI Skiba point. And I now have SETI Skiba point terminology in this book. You will find it somewhere. And some papers have used it, but it has different names, and I regret naming and not calling my paper MRAP. I met Skiba some time ago, and he was He was very deferential to me, but he also got a huge amount of benefit by being right terminology. Okay, I'll tell you why. So the concept of MRAP not being optimal is not there in the literature, because most literature don't use constraints. In economics, usually they don't want constraints, and so they go through this G bar, and the U bar is always feasible. And so I will give you 2 examples in this book where I will tell you that MRAP is not optimal. But again, it's not optimal. You can still call it MRAP. That is how the word is. Okay. So I also wanted to change the word double marginalization in supply chain coordination. I decided not to, because there are cases where double marginalization is not the right term. I wanted to call it nested optimization, but if I would change it, nobody will listen to me and nobody will change their terminology. So I also stick with double marginalization just like anybody else. So there are times when you should stay with the literature and there are times when you want to change it, but it's a tricky situation. Okay, so I will give you the example of what I mean by this soon, and you will appreciate what I was trying to do, but anyway, the literature did not appreciate. They appreciate, but they did not. In some sense, I did not get a good deal out of it. So while I will postpone this discussion of nearest feasible path, it's coming later. Well, maybe I should do it now. Oh, here it is. Let me do this right now. Suppose I have a control problem. So let's keep this slide. So I suppose it costs M dollars. So suppose if I put the advertising effort of 1 unit, the amount of money that I spent should be M times U, which is okay, which is not a problem. It's just a notation. So I will have the problem this way. And then let's assume that U is constrained by Q. Then my formula 7.11 will change to this. This is not a big deal. So I can find the G bar. It's not a problem. Okay. Now let's see the following idea. Suppose I did not remove this Z. If I don't remove this Z, then Z is an outside factor, temperature, weather, whatever, and it can go whichever way it wants in terms of time. And when it does that, then you will see that this G bar will depend on time. G bar, which is equilibrium, will still depend on time. It's a long run path, but it will be a long run path that depends on time, because Z depends on time. So if you do that, then let's do the following. Let's find the solution of this when Z depends on time. It's called G bar T. G bar T now looks like this. Here's G0. Here's G bar T. G bar T starts from here, goes like this, 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 goes like this. This is probably the only time that you will find the explanation of this idea. It's in my book, and maybe it needs more popularization, but people know it in some way, but anyway, this is what it is. So this is my G bar. Now suppose I start with G0 here. So what is the most rapid approach path? Well, the most rapid approach path is like this. Then it is like this. And then what happens? Well, at this point, I continue. So because remember, once I come here, I should follow this path. So I follow this path and I'm here. Okay. If I'm here, then if I follow this G bar, then my control is less than 0, because this slope is down much steeper. And U less than 0 is not allowed. So U0 will be allowed, and I will go along this path, and I come to here, then I can follow again this path, which is the path of G bar T. Okay, so if I was this place, and this is my initial condition, the most rapid approach path would be, if I'm here, but let's not worry about that right now. Okay, so I go this way. Turns out that this is not optimal because I waited too long to come here. What may be optimal is to start a little bit earlier and then use control 0, not here when I most have to, but do it when I don't have to, but I could. So I use 0 and I come here, and then I go here. It turns out that in this condition, this path is more, this path could be, in fact, such a path will be optimal. I have to find out where the C is, but such a path is optimal over this path. And the reason this is optimal is as follows. If you follow this path, you deviate from this G bar by this triangle. See this area? This area under the dotted curve and this line is a big area. Okay, and that is the deviation from the long run equilibrium path, G bar. Notice now, if I go this way, the deviation is defined by this part and this part. And it is possible that this part and this part is a lower cost because every deviation will cost you money. Because you want to be G bar. G bar is the best you can do, but the control does not allow you. So every deviation from G bar will cost you some money, and you want this deviation to be as little as possible in an integral sense. That means the cost of this deviation and the cost of the deviation should be less than the cost of this deviation. And in most cases, it will be. You have to find the right C so that that deviation is less than this deviation. Let's look at here. If I were to follow my G bar, then my control U star, which is U bar T, will go like this, and then it will go like this, and then it goes to negative, and then it goes like this, But this is not allowed. This is not allowed, then I will go, and you see, even this is not allowed. Okay, so I will then go U0, and there, then start here, I switch to 0, and I pick up the U bar again right here. So this one. So this is the new path. That path I call nearest feasible path because it's the nearest feasible path to the equilibrium path in some sense. So NFP was the term I put in there. Sorry. And it didn't sell. Okay. So this, and later on I will show you an actual example of optimal control where this idea is implemented in an example. Right now it is a concept, and the concept is very powerful. That there are times when MRAP doesn't work. So this is the first idea that way back when was realized in some sense, and I'm covering that in my book because I think that is an important idea. The next thing that I do is an idea called chattering control that has been around in the literature for a long time. And my first edition and the second edition of the book did not have that idea. So I have put that idea into this edition, which is called chattering control. And I'm going to now go to what is called the chattering control. So I already got you this part. You can already see the nearest, you see the nearest feasible path. All of that is done. And the papers that I mentioned to you, SETI 77B, which is, I think, the nearest feasible path paper, that is 1 year or 2 years earlier than the schema paper. And when you set the schema point in my book, you will see the schemas paper as well, and that. Okay. So there are some of the ideas in this topic. Now go to the chattering control. The chattering control, also called relaxed control, is because the cost of advertising is what? Why do I say convex advertising cost? The cost of advertising is concave, but the minus is convex. So the terminology here, I might have to think about it and change it. Let CU be the strictly concave advertising cost function with C0 equal to 0. So I'm now defining U is not linear, CU is non-linear. I will finish this and then we will leave. So CU equals 0, and then we can come back again later if necessary. C prime U is bigger than 0, C prime U is less than 0, so it's concave. And I have 0 less than UQ, which is Q is bigger than 0 is a bound. I have T bigger than 0. And so there is a new problem with the Q here and it's CU here, and I have a new problem, 7.15. Now, let's compare 7.15 to this. Notice, if I have this linear problem, then other than singular control, the problem has a bang-bang control. So the control is either 0 or Q. If it is 0, the cost is 0 here. And if it's 0, the cost is 0 also here. Right? So the problems are, as far as 0 control is concerned, the two objective functions are the same. What about when the cost is Q, the other part of the bang-bang? So let's look at that. So what I'm now going to do is relate this problem like this. So suppose Cu, the profit rate is pi g minus Cu, it's convex now. So actually it's a convex optimal control cost problem. It should not be convex advertising cost. This is not a good title. I will change that. Okay, so now boundary is 0Q, and we replace Cu by a linear function mu such that m is C divided Q by Q, so the mq equal to CQ. So C of Q will be exactly m of Q, which is m of Q right here. If I do that, then you can see that because of the concave nature of Cu, this function is convex because it's minus Cu. Then because of its convex, we know by definition that it underestimates this linear side on this side. And so this quantity is less than that quantity. Which means that if I do this, as far as the control is 0 and a Q is concerned, this is less than this. So I'm better off solving this problem than this problem, but they are identical if the control is 0 and a Q. But if the control is in between, they are not identical. If the control is in between, this gives me a better solution than this. So I'm better off with this problem than this problem. But this is my cost, not this. So my question is, what if I solve this problem and find a solution, and solve this and find a solution? This problem will be better objective function than this problem. So now the question is what to do. Is there any way I can get this objective function by solving this problem? Okay, so let's get to that. So here's what happens. We already talked about this. So suppose there are two small epsilons such that the G1 is above G bar and G2 is below G bar. Let's do the following. So this is my G bar. Okay. And this is my G1, which is epsilon above. This is my epsilon 2 below. And this is the path that is the most rapid approach path. So instead of going here, I go here. So I go a little bit above G bar. And then I use control 0 to go to this bar. Then I use control U to this bar. Then I control 0 to this bar. Now epsilon 1 and epsilon 2, I reduce them. If I reduce them, then I will go like this. If I reduce further, I will go like this. If I reduce epsilon 1 and epsilon 2 to 0, then in the limit, I will go here and then stay there. But I will stay there by using control 0 and a Q infinitely fast. So whenever I can have a coin, and the coin I will flip infinitely fast. Whenever the coin comes head, I use Q. Whenever coin comes 0, I use tail, I use 0. And I behave like this. I can actually achieve this. And remember, I'm using 0 and a Q. So by this idea here, I am actually doing better here than here. So I'm still in this problem, but I'm solving this problem by using chattering control, a control that switches infinitely fast. And by doing that, I am able to achieve the solution of this problem, which is equal to this problem. So what I'm trying to say is that for every epsilon, that solution is the near optimal solution. And epsilon equal to 0, it becomes the optimal solution. And this is also, if you learn the game theory, which somebody might have done, some people may not have, you will see a mixed strategy. Mixed strategy is this kind of strategy where you infinitely fast and do that. And you achieve a solution which is better than the solution which you could do by simply using U bar. See, if I use U bar to get, if I come here and go U bar, then I will be forced by this inequality to be not very good. So if I use U bar, I will have U bar here, and it will be less than this. But in the limit, if I use this CQ like that, I can actually make this equal in the limit. So that's the idea of chattering control. That means if I allow a control of this type, which is called chattering control, then I can actually do better than not allowing it. But if I allow chattering control, remember, if I do epsilon 1, which is not 0, and epsilon 2, which is not 0, then it is not kind of chattering control because I can implement that control. I can implement that. And that implementation will have a solution better than U bar, but not optimal. It will be better than this part. Better than this, but not equal to that. Equal only happens in the limit. So I can find a near optimal solution, which is a classical control, classical solution, and I can do better. So this is the idea of a chattering control. And it can be mimicked by putting V, where V is the probability measure, and it's a probability measure that switches infinitely fast. I have to find out exactly the V. I can solve this problem by using control theory. So when I solve that, I get V bar. This is the probability with which I should get a coin, which is not half and half. It's not a fair coin. It's a biased coin where the head and tail comes with these kind of probabilities, one with V bar, one is 1 minus V bar. And I should then implement that control based on the coin. And then I should be able to achieve what I need to achieve. So that's called the chattering control. We are infinitely fast. You can see here, we flip this coin infinitely fast and use maximum control Q when head come. Oh, when heads come up. So there's an S here that should also be corrected. Heads come up, and the minimum control 0 when tails come up, and so that's the idea of chattering control. I can, when there are questions about this, we'll come back to it again. I think we run out of time. And I will then go to this problem, which is where I use the Green's theorem. Please read this. This is one of my first papers in my thesis. This problem was published in Operations Research in 1977, I believe. And I learned of this technique that I use when I took a course at Stanford with a control theory guy named Breakwell, and I was a postdoc at Stanford under George Danzig. And once I learned that technique from this course, I applied to this technique and resolved my problem in the thesis, and then also published that paper later. Okay, so thank you very much, and we'll see you next week.
Thank you, Professor.
Thank you.
Thank you,
Bye.
Professor.
Bye.
Bye.